So to wind up this discussion on the design of a sequential circuit, let us also look at one example of a design using a T flip-flop. Okay. So basically we are going to assume that we are looking at a design with a T flip-flop. Okay. So first of all, just like we did, right, we saw earlier, we are going to start with a problem statement, get the state transition diagram, the table, the equations, and then the implementation, right. So let's look at the thing. We are going to look at a very simple case, which is a 3-bit counter. Okay, and I'll also make it very specific, up counter. Okay, so from the state 0 0 0, right, I am going to go to 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so I'm going to go like this. So here there is no input. I just want to go from one state to the next state like that, right? And of course, you're going to assume that you are going to reset and start at 0 0 0, right? And then from there it will keep counting, right, at the given speed of the clock, right? So first of all, how many flip-flops do you need? You obviously need 3 flops because there are 3 bits for you have 8 states and therefore 3 bits are needed for the states. Okay, so therefore what we are going to do here now is we are going to implement this with T flip-flops. Okay, like this. Okay, and I have the inputs A, B, C, flip-flop 1, 2, 3, right, and I have the clocks. Okay, as usual the clocks are running like this, right, and I have inputs are TA, TB and TC, right. So all I have to figure out is what is this combinational block 1 where the inputs are A, B, C and the outputs are going to be TA, TB and TC, right. So obviously I'm going to start with my present state. Okay, A, B, C and next state, right, A, B, C, right, and there is no there is no input, so therefore we just stop with these variables, and then I need to figure out flip-flop inputs, right, TA, TB and TC. Okay, so if it is 0 0 0, you go to 0 0 1, 0 0 1, you go to 0 0 2, I mean see, you go to 1 0 1 0, 0 1 0, you go to 0 1 1, 0 1 1, you go to 1 0 0, 1 0 0, from 4 you go to 5, 1 0 1, you go to 6, 6 you go to 7, from 7 you go back to 0, right. So this is the next state that we need, And obviously, in order to get the TA inputs, we start with the characteristic equation table of T flip-flops, right? We are talking of T and Qn plus 1. If it is 0, it is Qn. If it is 1, it is Qn bar, right? And so you can build an excitation table, right, which is basically current state, uh, and next state 0 0 0 1 1 0 1 1, right? And then you're going to tell me what the input is now, right? That's what an excitation table is all about. So if it is 0 0, you want it to stay where it is, so it's 0 0 1, you want it to toggle, so T has to be 1 1 0, again you want it to toggle, so T has to be 1, and 1 1 you want it to stay, so this is the excitation table, right? So now, in order to figure out TA, TB, TC, we need to look at the corresponding things, right? We start with the A, it's at 0 0, that means this is the case, 0 0, this is 1 1 1 is again 0 0 0 and 1, right? This is what we have for this thing. TB is basically going to be again 0 0 is 0 0 1 is toggle, 1 1 is same, 1 0 is toggle, 0 0 is same, 0 1 toggle, 1 1 is same, 1 0 is toggle. TC is going to be 0 1, which is toggle, 1 0 is toggle, toggle, 1 0 again is toggle, 0 1 toggle, 1 0 toggle, 0 1 is 0 1 is toggle, and TC. Oh, interesting. So basically what we have is the TC input has to simply be connected to 1 always, right? Because you just have to keep toggling that flip-flop output always, right? On the other hand, TB is toggling every alternate this thing, and TA is toggling every four times. So TB is toggling every other cycle. A is toggling every 4 cycles. Okay. So if I look at this circuit now, right, I will take this. So my TA is summation min terms 0 1 2 3 3 comma 7. TB is summation min terms 1 3 5 7, and TC is basically just 1. I don't care about the min terms because it's always 1, right? So if I want to solve for TA and TB, right? So B bar, I mean B and C, right? I'm going to write out the K map now. B bar C, BC and BC bar, A bar and A. 0 1 3 2 4 5 7 6. So what do I have now? TB is 1357. Okay, TB is 1357. So I have a nice set of 4 here. So this is for TB. So TB is equal to C. This is very nice, okay, and then I also need to, let me copy this. For TA, right, I am now talking about TA is 3, 7, right. So therefore, I have this. So I am done here and I will get TA equals BC, okay. So effectively, if you look at the implementation of this whole thing, I'll be talking about okay, I'm going to call this as C, by the way. This toggle flip-flop is just connected to 1. TB, okay, this is my C, B and A. This is my TB and this is my TA. So if you look at this, the clocks, I will show it as running underneath like this to not clutter the diagram. TB is like this, right? TA is just B and C. So right, okay. So flip-flop 1, 2, flip-flop 3, right. I hope I got the numbering. No, flip-flop, okay, it should be the other way around. Flip-flop 3, 2, 1, exactly. So this is your toggle flip-flop based binary counter that just goes from all the way from 0, 0, 0 to 1, 1, 1, right. So this is actually, it is not that surprising, okay. If you look at the implementation, right, if you want to intuitively understand this whole implementation, you look at TA, TB and TC. What is it saying? It is saying that the TC, which is the least significant bit, should toggle every clock cycle, right. On the other hand, your TB should toggle every other clock cycle, right, and TC should toggle every 4 clock cycles, right. So that's the idea that we are talking about here, right. So if you look at it, if you just look at the waveform, right, that you want as a function of time, if you look at C, B and A, right, uh, let me plot this with respect to the clock. I'll move this up, TA equal to BC, okay. So I'm going to look at 8 clock cycles. Okay, these are my sampling edges. One, two, three, four, 5, 6, 7, 8. Okay, I'm not drawing this to scale. So you look at this, I have right. So if I simply plot my ABC that I wanted, right? So I want A to start with 0 0 0, ABC to start with 0 0 0, and then sorry, I'll plot C here, okay. And then I want the state to go to 0 0 1, right. So B continues to be 0, A continues to be 0, okay. So this is 0 0 0, 0 0 1, right. Then I want it to go to 0 1 0, then 0, sorry, 1 1, right. So 0 1 1, okay. Then I want it to go to 1 0 0, 1 0 0, 1 0 1, right. And finally 1 1 0, and then 1 1. So if you look at the way this binary counter, right, you just look at these values. This is my states. It's going through 0 0 0 0 0 1 0 1 0. So if you just look at this waveform here, it's very evident that C has to toggle every clock cycle, right? And therefore all you have to do is connect TC to 1, make it toggle every clock cycle. Now TB has to toggle every 2 clock cycles, right? And therefore you just give the C as the toggle input to it, right. So whenever that whenever that happens, you will find that this B also is going to is going to toggle there, right. And then you basically do the other case of uh, when both B and C are high, right. Uh, then you basically make this A toggle, because that has to toggle every 4 clock cycles, right. So in some sense the solution we have got is very intuitive, and you could have looked at this diagram and actually made the entries for that flip-flop TA, TB and TC as well, right. So with that I will wind up the discussion on the design of sequential circuits using various kinds of flip-flops. Thank you.